Okay, so what I want to tell you now is that in the last video we seen a formula that allowed us with as norm to see what we want from the output. It was just the sum of x or the probability of px of like what you have minus like we wanted to have in a way like cx minus decoding and coding of it being like equal to 0, but because it's we can have like little mistakes, it's equal to this, and because we sum over different sources, which each of them having px, with x going to x1 to xn, we had this, and but it's really hard to compute mathematically the trace norm. Um, and so, yeah, the idea here is like to try to find something that could be more easier to calculate, and that's purification. Because like we're trying like to track like do we have a classical probability problem, and we just want like to go to a quantum geometrical problem. So it's basically going from mixed state to pure state. And to do this it's just called purification. Like, do not mistake me, please. Like, a mixed state is still a quantum state, but it's just like we transform mathematically. Like, there's still like classical into it, it's just like we have 1 chance over 2 having 0 0 plus 1 chance over 2 having 1 1, but we transform it into the superposition 0 plus 1 over square root of 2, which is like a really 100% quantum mathematical property. Because we can be able to use more powerful mathematical tool on pure states because they have wonderful properties such as the fact that we can represent them by vectors, or we can calculate the scalar product, or we can use Schmidt decomposition that mixed states do not have. So basically, if we want like to represent it for a same polarity, like here for a pure state, for a mixed state, this would be like 1 over 2 0 0 plus 1 over 2 1 1. Where here it's just like 0 plus 1 over square root of 2. And so, yeah, you see like that here we really have in the first case, like in the second case, Schrödinger cat, 100% quantum randomness. Well, in the first case, like it just it's still a quantum state, mixed state, but we have like some classical randomness. There is like, yeah, can like have a coin, its head or tail, and we can have this. So yeah, we say like for mixed states, it's a quantum state where we have still classical randomness and quantum randomness, because like if you measure in the same preparation your mixed state, then it will be like still a classical randomness. But like if you measure a different basis instead of 0 and 1, measuring into plus or minus, then you create quantum randomness, quantum pure randomness. So yeah, that's why the mixed state like has a two type of randomness, quantum and classical at the same time. while into the pure state it's fully 100% quantum randomness. Yeah, like as I said, we have more properties like into the pure state, because mixed state, like we can use density matrices, probability, some probability rules, like, but with mixed state, with pure states, we have some other tools, such as the fact that we can use vectors, string decomposition that does not exist with mixed states. So yeah, the idea of purification is just to take a new system R that will less or more stock the information about it and have a copy about it, and so with it, it will work. So at the beginning, if you remember, we had like a row which is equal to sum of x of px of px px, and so now the idea here will be like to say, instead of writing it like this, the 0 0, we don't care about that. We just want like to say like, no, our state will be written like px of a, for example. So we can go from density to mixed state to pure state with purification. So yeah, we can say like it can be written like this, for example, and we take the square root of the px because that's how we calculate amplitude probability squared, like after in quantum. And so take this in the case of we have like, our example a b b b b b, then we do not care, we can like stock here and stock here. It's only a and b, so you can stock the same. So after you can just check about r if it's the same of a, and so if there was a mistake on a during the trick. And but if you have like a count and like you have 0.10 plus 0 plus 1, like 1 over 2 plus rising over 2 divided by 3 for x air. So because it should be orthogonal, it will not work, like, because you will not have like an orthogonal set. So the way to remember about it is just to say, take px, but we take the index of each step, so we have an identification of what represents what. So that's how we can represent it. And so that's the definition of a purification of A, where we introduced a system R to do some entanglement about it and having a pure quantum randomness. Because like we should be really able um, to compress, to crypt, no matter what, even if the quantum source should be like really weird, like we still have it into A, like we preserve it, but into R, like we just have perfect memory, like know exactly 0 R, 1 R. So in the case of the stuff, if you have like racine of P 0 0 0 A 0 0 R plus racine of P1 of racine to 0 plus 1 over 2 of 1, then you just take like 1 R, like, because x is equal to 1, x is equal to 0. It's clear, even if there is no orthonormal stuff here, it will still be. So yeah, that's why it's x and not psi of x. And because we saw earlier, like we had another video that PA is equal to PA to the N. Here we just have PAR um, of N. Um, anyway, like N, then it just equal to PAR XOR N. Like we can decide to call PAR to be like our C, and so yeah, we can have like this. At the end, we have just this is equal like to we have like this being a purification of PA XOR N. So yeah, basically. Um, where you can write that okay, so basically if we take an example like about your AAA BBBBB, so we'll just have after like A B B B B B of A, so A B B B B B. Okay. Well, here in this case, I told you that the particular case, like we don't care because it's the same, but with the coin, like it's x and not necessarily x equal x. We just need after to verify like the message written to the end is like synchronized with is one of R, and if we take like a head or tail, like we have like 4 qubits, and we just want to say 0 0 0 0 0 R plus rise in the square root of 1A 1 R. Then we have we just have the X here, and yeah, it will work great about it. Well, to be more accurate, like it will be more 1 here, like because just all the other would be like racing of 0 stuff. Here is racing of 1 because we're through the message, so it's 1, so we have this. But anyway, if we take our stuff, now like we'll have in a way C of A X or N, and this at the end is just in a way like qubit A1, like by just like A1 XOR R1, XOR A2 XOR R2, XOR AN XOR Rn, and it's an alternated order, but for the rest of the code, like the encoder will take all real qubits A in one time to compress them, while the R ones will not move and will stay in their side. And it will be like really awful to read visually if we mix them. So we just decide to rearrange them to have all real qubits at the left, and all the ones that trying to copy them at the right. All the A will be there, the copy, the This, if I can allow myself to say this, will be on the other side. So this will go to the one to compress, them will be stay identical. It's notation abuse in a way, uh, because like to change normally the order of tensor predict, we need to apply permutation metrics, but we can allow it for like writing style. That's why we say there is some abuse of notation when we write this, because you now need a matrix of permutation. But yeah, that's it. And so yeah, the idea is just to introduce R stuff, and saying okay, this will not change. We are the a power of n, it will change sort of stuff with the encoding and the decoding, and so after the encoding you have b power of m, with m being normally as low as possible, still conserving the accuracy, because if you compress and you lose information, then just don't put information, it has your information to be more compressed. So yeah, still need and so externally you just have to have the same thing as more, which is like just for the stuff itself. At the end you have this, like more at the beginning you have this. After you encode it with a link to bm, the decode from b link to an, and yeah, having the final stuff. So yeah. As you see, like the channels act does not act on the R system, just on A. And so the new formula we have about just that the same. We have like rho r 0 n minus d epsilon minus the decoding encoding for r 0 n inferior to delta. Here we just normalize with 1/2, so it's between 0 and 1, because before we did not did it, but we could have done. And the other thing we can notice is that in the first formula, like we have sum of x of px, but here we do not have, because it's not mixed state, it's pure state. It's like that's the difference between the sum of x of px, px, whereas the head and tail stuff, when you have either 1/2 0 0 0 or 1/2 1 1, or a really pure integral stuff where we don't know if it's 0 or 1 now for so it can be like it's a mixture of both, so there's not the sum stuff, and so that's why we don't put the sum of x of px. Or maybe I seem to be like really accurate, like at the beginning we should have put in reality the 1/2, it was not really rigorous to say because like here we could have like put 1/2 to be really accurate and having like between 0 and 1 a real probability to respect Schumacher theorem that we'll see after in other videos, I think. But yeah, that's it.